Hi, I'm Kathy. In this lesson, we're going to look at some of the theory of polynomial equations. Our specific objectives are complex numbers, quadratic equations with complex solutions, the fundamental theorem of algebra, and polynomial equations with complex solutions. Let's start with a couple of definitions having to do with the imaginary unit I. Properties of the imaginary unit I. First of all, I is equal to the square root of -1 because I squared is exactly -1. And so if we have an expression like the square root of -a, as long as a is greater than 0, then we can write the square root of -a as I square roots of a. Let's try this out. What we want to do is simplify some different expressions. Let's start with the square root of -16. According to that second statement on the previous page, this is the same as I square roots of 16. And I know that the square root of 16 is 4. And conventionally we write I times 4 as 4i. In a similar fashion, the square root of -11 can be written I square roots of 11, and if an I is multiplied by an expression in a radical, we usually leave the I on the left so that it doesn't look like it's in the radical. Now the square root of -20 can be written I square roots of 20. Realize that the square root of 20 is the same as the square root of 4 times 5. There is an exact square root of 4, and we can take that exact square root of 4, which is 2, write it outside of the radical with the I, and leave the 5 in the radical. We're going to continue from here to define complex numbers. A complex number can be written in standard form as a plus bi. This is not a sum of complex numbers, but one complex number, where a and b are real numbers. The real part of that number is a, the imaginary part is b. What we want to be able to do is operate with numbers like this. So let's practice some operations. We're going to write each expression in standard form, support our results using a calculator. But first we'll find each calculation. And the first calculation we want to make is to sum the two numbers, -3 plus 4i and 5 minus I. Removing the parentheses, this can be considered -3 plus 5 plus 4i minus I. Then combine what look like terms. The real parts add to 2, the imaginary parts to 3i, and that's the sum of the complex numbers. We'll support that with the graphing calculator in a minute, but let's try another operation. Here we want to find the difference, -7i minus 6 minus 5i. Removing the parentheses this time, I have -6 plus 5i, and rearranging the order, the real part can be written first, then the two imaginary parts, which then can be combined to give me the complex number, -6 minus 2i. Let's try another operation with complex numbers. Here we want to square the number -3 plus 2i. Treat this as -3 plus 2i times -3 plus 2i, and apply either the distributive property or the FOIL method. -3 times -3 is 9. -3 times 2i is -6i. 2i times -3 is -6i. 2i times 2i is 4i squared. Now I see that I have like terms in the middle that I can combine to get -12i, and recall that I squared is exactly equal to -1. Now I have some terms that I can combine. I have 9 plus 4 times -1, which is -4. Combining those gives me 5 minus 12i. And let's do one more operation on complex numbers, and then we'll check all the ones we did on a calculator. Here I want to divide 17 by 4 plus I. There's a little bit more involved with division of complex numbers. The procedure is to look at the denominator, figure out what its conjugate would be, which has the same terms but opposite sign in the middle, in this case 4 minus I, and multiply the numerator and denominator by that conjugate. So multiplying numerator and denominator by the conjugate of the denominator. Using the distributive property in the numerator, 17 times 4 is 68. 17 times minus I is negative 17I. Multiplying out the numerator, I have 16 minus 4I plus 4I, and then I'll have minus I squared. Continuing, mostly simplifying the denominator, I end up with no I to the first terms, those add to 0, and I can replace I squared with negative 1. So the denominator is going to simplify to 17. And to simplify further, consider 17 divided into each part of the numerator. 68 divided by 17 is 4. 17 divided by 17 is 1. And I've divided. The result of this division is the complex number in standard form 4 minus I. Well, let's check each of those 4 operations with the graphing calculator. One nice thing about a TI-83 is that there is an I on the keypad above the decimal point. So we're going to use that I. The first operation we did was negative 3 plus 4I, and then I had that plus 5 minus I. Pushing enter, I get the result 2 plus 3I, and you can confirm that that's what we got when we actually did the division on paper. Our second operation was 7I, negative 7I, got to put the right thing in to get the right answer, minus the complex number 6 minus 5I. The result is negative 6 minus 2I. And then we performed the operation negative 3 plus 2I, all of that squared. And finally, we performed the division, 17 divided by the number 4 plus I, and we got the result 4 minus I. Well, let's continue, but put i's in complex numbers into the realm of quadratic equations. Here's what we're going to do. We want to solve the quadratic equation 3x equals 5x squared plus 1. Well, you know that anytime you solve a quadratic equation, you need to set it equal to 0. So let's do that here by subtracting 3x. And we'd like it to factor, but it's not going to. So we're going to go immediately to the quadratic formula. A is 5, B is negative 3, C is 1. So we'll write x is negative 3 plus or minus the square root of negative 3 squared minus 4 times 5 times 1 divided by 2 times 5. And we'll continue by simplifying. The numerator is 3 plus or minus the square root of 9 minus 20 divided by 10. Continuing inside the radical, 3 plus or minus the square root of negative 11 divided by 10. And here's a negative number in the radical. What we do is pull the negative out of the radical and represent it by the symbol I. And so we'll write these solutions as 3 plus or minus I square roots of 11 divided by 10. We stop here with this particular equation since nothing simplifies. If 3 and square root 11 and 10 all had a common factor, we'd continue. Well, why don't you try a problem like that? Here's what I want you to do. I want you to solve the quadratic equation 3x squared plus 5x equals -4. Stop the tape and try this and restart when you're ready to check your work. Well, let's see how you did. As with the previous example, we need to set this equal to 0, so I'm going to add 4 to both sides to set it equal to 0. It'd be ideal if it factored, but it doesn't, so we go immediately to the quadratic formula. X equals -b, which is 5, plus or minus square root of b, which is 5 squared, minus 4 times a, which is 3, times c, which is 4, all divided by 2 times 3. Continuing, we simplify the numerator sum, -5 plus or minus the square root of 25 minus, now this is 12 times 4, which is 48, all divided by 6. Continuing by doing the subtraction in the radical, have -5 plus or minus the square root of -25 minus 48 is 23, divided by 6. And again, we have a negative number in the radical, so we write our result as -5 plus or minus I square roots of 23 divided by 6. And those are the two solutions to the quadratic equation. Well, let's continue in this lesson and look at something called the Fundamental Theorem of Algebra. The Fundamental Theorem of Algebra states a polynomial f of x of degree n greater than or equal to 1 has at least one complex 0. And there's an additional theorem that's really helpful to use in conjunction with the fundamental theorem. It's called the number of zeros theorem. A polynomial of degree n has at most n distinct zeros. Well, let's see how we might use those. Here's an example. What we want to do is solve the polynomial equation x cubed minus 5x squared plus 4x minus 20 equals 0. Well, solving this equation is analogous to finding the zeros of the polynomial that is the left-hand side. So if you think about the two theorems that we just looked at, they give us the information that since this is a third-degree polynomial, we're looking for 3 zeros. Well, let's start with a graph of that and see if we can get any information at all about it. Zeros. Remember, a zero is the same thing as an x-intercept. So let's see. We'll go into the y equals part of our calculator and put in x to the third minus 5x squared plus 4x minus 20. And let's see what kind of window we have. And see if we can get a decent graph or any information at all on a standard window. Well, that's not much of a graph, but we're not interested in the graph of the polynomial. We're interested in its zeros or x-intercepts. It looks to me like it has, or this particular polynomial, has a 0 of 5. Well, what we'll do is we'll use some synthetic division to determine if 5 is actually a 0. But remember, we're looking for 3 zeros, not 1, so finding 5 is not going to be sufficient. But it'll be a start. So 5 is our synthetic division divisor. The coefficients of the polynomial are 1, -5, 4, -20. Bring down the first coefficient, multiply it by the divisor, write the answer in the next column. That sum is 0. Multiply again by the divisor, find the sum. That sum is 4. Multiply by the divisor. That product is 20. And I get remainder 0, which confirms what I thought from my graph, that 5 is 1 0. I'm looking for 2 more zeros. Remember that this number is the remainder. And what I've determined so far about this polynomial is that it can be written x minus 5 times this quotient, which written as a polynomial is x squared plus 4. So in a sense, I've factored my polynomial equation to this point. I know the solution that comes from the factor x minus 5. So let's get the rest of the solutions by setting the other factor equal to 0. Subtracting 4 from both sides of this equation, I see x squared is negative 2. Taking the square root of both sides, x is both positive and negative the square root of negative 2. I don't leave the negative in the radical. I write my result as plus or minus I. Actually, I made a mistake, didn't I? This is a 4, and I wrote negative 2. So let's redo that part correctly and say x squared is negative 4. So taking the square root of both sides, I get plus or minus the square root of negative 4. And for the negative, I'll write an I. The square root of 4 is 2. So the two solutions from this factor are plus or minus 2i. The three solutions to this polynomial equation then are 5, 2i, and negative 2i. The solutions are 5, 2i, and negative 2i. Let's try another example that uses those theorems. What we want to do is represent a polynomial f of x of degree 4 with leading coefficient 3 and zeros of negative 1, 6, 5i, and negative 5i. Notice the 4 zeros in completely factored form and then in expanded form. So essentially we want to write down a polynomial using this information, first in factored form, then expanded form. Well, let's see. We need degree 4, we need a leading coefficient of 3, and we need these zeros. Considering the zeros, first of all, here's my polynomial symbol f of x. Each zero contributes a factor. Negative 1 contributes the factor x plus 1, 6 the factor x minus 6, 5i, x minus 5i, and negative 5i, x plus 5i. But I want a leading coefficient of 3. Now I have a leading coefficient of 3 because 3 will multiply the highest power of x. And I need to make sure I have degree 4. Notice that x is to the first power in each factor, so that product of x's will give me x to the 4th. Here's the factored form. I also want expanded form, which means I need to multiply these factors together. Let's start by multiplying the two factors that have complex zeros in them. So I'll keep my 3, my x plus 1, and my x minus 6, and I'll multiply these two factors at the right. I'll get x squared plus 5i minus 5i, and then minus 25i squared. The 5i's are going to add to 0, so I still have 3, x plus 1, and x minus 6. The 5i's, as I mentioned, add to 0, and this is negative 25 or minus 25 times negative 1, which I can write as x squared plus 25. Now I've got to keep multiplying, so let's continue with this. This is f of x. Let's multiply x minus 6 times x squared plus 25. So we'll hold on to our 3 and our x plus 1, and we'll use the distributive property or FOIL method here. I get x cubed plus 25x minus 6x squared minus 6 times 25, which is 150. If there were any like terms here, I'd be sure to combine them. There aren't any, so I'm going to continue multiplying by distributing each term in x plus 1 to each term in this cubic polynomial. So I have 3 times x cubed, x to the 4th, x times 25x, which is 25x squared, x times negative 6x squared is negative 6x cubed, x times negative 150, negative 150x. Now 1 times each term, x cubed plus 25x minus 6x squared minus 150. Now there are some like terms, and I'd also like to write the polynomial in descending powers of x. So I'll start with my x to the fourth term. There's only one of those. I have minus 6x cubed plus 1x cubed is minus 5x cubed. 25x squared minus 6x squared is 19x squared. And minus 150x plus 25x is minus 125x. And finally, my constant term, negative 150. As a final step, I'll distribute my leading coefficient of 3 to get 3x to the fourth minus 15x cubed plus, let's see, 3 times 19 is 57x squared minus 375x minus 3 times 150 is, let's see, 450. And so here's my polynomial that fits all the criteria in the example. Well, in this lesson, we've done a number of things with polynomials and polynomial equations. Be sure to work lots of exercises from your textbook for practice.